This is a walkthrough of Problem 3 on Exam 2 of Module 5 in the book Problem Solving Guide for Mechanics and Thermodynamics. An elastic cord has a relaxed length of 1 meter and a stiffness of 50 newtons every meter, which is also a half a newton every centimeter. One end is attached to the ceiling, 2 kilogram mass is suspended from the other end. How far does the cord stretch with the 2 kilogram mass suspended from it? Part B. The 2 kilogram mass is pulled down until the cord is stretched 1 meter and held there. What is the tension in the cord? Now it's let go. What is the acceleration immediately after it's released? Part D. What is the speed when the cord goes slack? Part E. What is the maximum height the mass reaches? Part F. What is the maximum speed of the mass on the upward trip? Seems like a long one. Let's start with a good diagram. So there's our cord. Its mass is hanging from it. The relaxed length is 1 meter, and there's some stretch, which we don't know. That's X, and that is part A. What's the stretch when a 2 kilogram mass hangs from this cord that has a stiffness of 50 newtons every meter? It's just hanging there. It's stationary. The force of gravity must balance the tension in the cord. The downward force of gravity on the 2 kilogram mass is mg. G is 10 newtons every kilogram. The weight of that mass is 20 newtons. The upward force the spring exerts on the 2 kilogram mass must also be 20 newtons. And we can set this equal to kx because the force a cord exerts is k times x. So we have the force of 20 newtons is kx, and we know k is 50 newtons every meter. So we just divide both sides by 50, and we solve for x. 0.4 meters, which is 40 centimeters. On to part B. Now the cord is pulled down until it's stretched 1 meter. So let's adjust this diagram. Move the mass down. X is 1 meter. The total length of the cord is 2 meters. Somebody's holding it there. When they let go, it's going to go flying. There's 3 forces on that mass: gravity, the tension, and somebody hanging on to it. All we need is the tension of the cord, and that's kx. K is 50 newtons every meter. X is 1 meter. The tension is 50 newtons, and that's part B. Straightforward so far. On to part C. It's released. What is its acceleration? So there's 2 forces on it, gravity and the cord. The person hanging on to it isn't exerting a force because she let go. The force of gravity is 20 newtons downwards, as always, unless this thing goes into outer space. The force the cord exerts, we just calculated it, is 50 newtons upward. The net force is 30 newtons upward. We set the net force equal to ma. M is 2 kilograms. The acceleration is 30 newtons divided by 2 kilograms, and that is 15 meters per second, and it's a vector, so we should say upward. Part D asks for the speed when the cord goes slack. So it's going to accelerate upwards, and then the cord's going to go slack after it goes 1 meter. Because the relaxed length of the cord is 1 meter, the acceleration is not constant over this 1 meter ascent. So we can't use, for example, v final squared equals v initial squared plus 2ax because the acceleration is changing. So we use the work energy theorem. Let's adjust the diagram again. We want to know the speed when the cord goes slack. Right there, that thing's moving upwards. How fast is it going upwards? It went upwards, so gravity did negative work on it. The gravitational force is downwards. The force gravity exerts is mg, and it went up 1 meter. So we can calculate that gravity did minus 20 joules of work over that 1 meter. The cord is pulling it in the direction it's moving, so it does positive work on the mass, and that is 1/2 kx squared. So 1/2 50 newtons per meter for k times 1 meter, that's plus 25 joules. So the cord did plus 25 joules of work on the mass. Gravity did minus 20 joules of work on the mass. The net is plus 5 joules, and that's the change in kinetic energy. So the mass has 5 joules of kinetic energy. It started from rest. So we can solve for V final, and it's the square root of 5, which is 2.24 meters per second. So when the cord goes slack, it's going 2.24 meters per second. That's part D. Part E is what's the maximum height the mass reaches. So the cord is no longer in play, it's slack. The mass is moving upwards at a speed of 2.24 meters per second, and we have to get the maximum height. So let's put that on the diagram. H max is moving 2.24 meters per second upwards. How high does it go? The cord is slack. The only force is gravitation, and that's a constant force. So we can use, for example, V final squared equals V initial squared plus 2ay. V final is 0. V initial, 2.24 meters per second. Acceleration is minus 10 meters per second squared. Downward, we can solve for y, and we get 25 centimeters, 0.25 meters. That's part E. Now part F. Pull down 1 meter. We let it go. It speeds up. Cord goes slack. We want to know the maximum speed on the upward trip. Somewhere the speed's going to be a maximum. You let it go, it's accelerating at 15 meters per second squared up, and then eventually it stops. There must be some point in there where its speed is a maximum, and we have to find it. We're going to have to think a little bit here. What the heck's going on? We release it, it accelerates upward at 15 meters per second squared. Eventually, the gravitational force is going to get bigger than the tension in the cord. Initially, the tension in the cord is bigger than the gravitational force. It accelerates upward. When it does, when the gravitational force exceeds the tension, the mass is going to make this transition from speeding up to slowing down. And when it makes that transition, it must be at the maximum speed. If it goes from speeding up to slowing down, it's not going to get any faster. That point is when the speed is a maximum. We've already found this point in part A. Part A says, when do the forces balance? When the cord is stretched 40 centimeters. Right there. Right here. This is where the speed's a maximum. It's speeding up from here to here because the tension is bigger than gravity. Above that, gravity is bigger than the tension. So now we have to calculate the speed when the cord is stretched 40 centimeters. So it went 60 centimeters upward. Gravitational force does minus 12 joules of work on it. mg delta y, minus 12. So now we got to figure out the deposit that the cord made into the mass's kinetic energy. From a stretch of 1 meter to a stretch of 40 centimeters, the work the cord does is 1/2 kx initial squared minus 1/2 kx final squared. It doesn't use up all of its energy. It just goes from 1 meter to 0.4. So we can calculate these. 25 joules, we did that before. There's 4 joules left that didn't get used, so there's 21 joules. The cord made a deposit of 21 joules into the kinetic energy. Gravity made a withdrawal of 12. The net is 9, and that's the most kinetic energy the mass is going to have on the way up. The mass started from rest. If the kinetic energy change is 9 joules and it started from rest, it must have 9 joules. So we can set 9 joules equal to the kinetic energy, and this is the square root of 9 joules over kilograms, and that's 3 meters per second squared. And I like that answer because when it gets to 1 meter, it's gone 2.24. So the maximum is 3 meters per second squared. 3 meters per second. Makes sense. Whew, that was a long one.